All right, so again, I am Nick Luchenko. I'll be talking about my work with Gautam Kaki and Prashant Praladhan at CU Boulder, and presenting a new way of providing convergence for replicated data types using runtime assistance. So as many of you know, replication is a technique for scaling applications where you have multiple machines or data centers that each keep a full copy of the state and use that state to serve users that are local to them. Eventually, changes that come from that are propagated to other locations, and this is fairly straightforward until you have concurrent changes or conflicting changes. And then you need some kind of conflict resolution technique to resolve those conflicts. There's many properties you might want for how this works, but one thing you probably want is convergence. You eventually want all locations to agree on the same final state. So also, as many of you know, mergeable replicated data types are one technique for providing this conflict resolution. So these are also MRDTs. MRDTs use a three-way merge function, essentially generalizing gets three-way merges on file conflicts. And this merge function uses information about the history of the execution to identify what is new in the conflicting states and what should carry on to the resolved state. So this history information is called the latest common ancestor, or the LCA. So to give a concrete example, here is the set MRDT, where the idea is that the merge function identifies what has been newly added or newly removed in states, in the conflicting states, and then carries those forward into the final state. So here we have a simple execution with two replicas, where we start with the set containing A, one of them removes A, and the second one adds B. So then the merge function takes a look at those states and then compares them to the latest common ancestor, in this case the only common ancestor of the two, to see that the absence of A is new and the presence of B is new. And so both of those carry over to the final state, and we get the set containing B. So this is nice. MRDTs kind of help us get sensible conflict resolution, and they do it while not complicating the states. So we don't have to add convergence-related metadata about where changes came from or how many changes have occurred in the states. And so that means that we can use standard software to edit the states, like your favorite text editor or some kind of optimized set manipulation library. These things don't need to know about replication. They just make the edits, and then the replicated store does all the work in the background. But what about convergence, right? What about that property that we probably want? For an arbitrary merge function, does any execution of edits and merges result in convergence for all of the different replicas? The answer, unfortunately, is no, and I can give you an example here, again, using the set RDT. MRDT. So here we have three replicas. One of them removes A from the initial state. We fill in our merge function. This removal of A is seen as the new information, so we get the empty set here. And meanwhile, another replica might perform the same change, also removing A, and send that off to replica 3 over here. So in this case, the conflicting states are actually the same. They're both missing A, and so the result is also missing A. So if this kind of twisty shape of the arrows is making you suspicious, you have the right intuition. Now we could add A back again. Here now the presence of A is the new information because the LCA between R2 and R3 is no longer the initial state. It's now this empty set state. And we finally get into trouble when we try to merge the final state of R2 into R1. Now we have to go all the way back to the initial state for the LCA because R1 and R2 have not seen any of each other's changes up until this point. And so the absence of A that R1 knows about is seen as the new information. So now we have two states that descend from all the changes in the graph, and yet have come to different conclusions about what the final state is. So this isn't what we want. What could we do to get convergence then? Well, one way is we could look at our merge function, and we could try to engineer a proof that our merge function's behavior will guarantee convergence. And that's not our favorite solution, partly because proving properties is hard. I think everyone's aware of this. And also, sometimes you just can't really. Like, we just saw this set MRDT that we might want to use, and we've shown that it doesn't provide convergence. So if we actually wanted it to do that, we would have to add more information to the states, more information to the merge functions, like unique IDs or something. And then we've lost some of this nice property of being able to use standard software to edit them. Now, parts of the state are not just purely sequential. They're these special values that can only be edited in special ways that are related to the replication. So if we don't want to do this, then we don't want to touch the merge function. What else could we do? Well, the other thing that we can look at is the execution. A common way of getting all kinds of properties for replicated data stores is to restrict when and where edits can occur in the system. So we might have a rule that says only one thread at a time can make edits. That's straightforward. It will give us convergence in a straightforward way, but it will slow things down because some threads will be waiting for the opportunity to make their edits. And if some kind of partition occurs, then whoever is stuck on the outside of that partition is going to completely lose their local editing experience because they won't be able to make any changes at all for a while. Another thing to note here is that if we're following this approach, we never actually really use our MRDT merge function. We only do these kind of fast-forward merges where the LCA is identical to one of the states and only one of the states has changed. So this suggests that we're not really leveraging MRDTs here, and that maybe since we have these nice merge functions, there's a better solution. So to get to that better solution, we make an observation here about LCAs. So if we look back at our divergent execution example, and we think about, like, what if we wanted to merge these two divergent states together? Well, the first step in doing that would be to identify what is their LCA. So this is an obvious candidate here, V1. It is a descendant, or it is an ancestor of both these states, and it's the furthest down in the picture, so it's probably the LCA. But actually, there's a second one that is also an ancestor of both, and it's not causally related to V1. Neither V1 or V2 have seen each other. And so it's actually also an LCA. So in fact, we've shown that this condition of having two LCAs between two states is necessary for those two states to have diverged. So then that leads us a little further along our path. We've identified this condition of requiring these two LCAs. If we can prevent that from happening, then we can prevent divergence. And so a nice thing about LCAs and trying to prevent LCAs from occurring is that we can do that both by restricting the appearance of edits, but also instead by restricting the appearance of merges. So if we look at this graph, we have our paths going back to both these LCAs. And clearly, if we could go back in time and prevent one of the links on these paths from occurring, then we could prevent that second LCA from occurring and thus the divergence from occurring. So sure enough, if we take out this merge from the graph, the result on R1 would have been the same as the result on R3, and we have convergence. So that's the approach we use, and we formalize this in an abstract machine for MRDT executions that we call Quark. And Quark is able to guarantee convergence by delaying merges. And by doing that, it can give you zero latency edits. It never restricts edits from occurring. And it also allows you to use arbitrary merge functions. We don't need to prove any algebraic properties. We don't need to add any kind of metadata to our states. So to just give a sense of how it does this, we can look at the core rule that is enforced for performing merges in Quark. So essentially here, if we have two replicas, R1 and R2, and we want to merge them, what we have to do is consider every other branch, R3, and consider the LCAs between R1 and R3 and R2 and R3. And what we require for these is that one of them be an ancestor of the other. They have to be related. And the reason for that is that once R1 and R2 have merged, that resulting state, if you consider that with replica 3, the LCA between this merged state and replica 3 is going to be one of these LCAs in the picture here. And if they're not related, it's going to be both of them. And thus, divergence would be allowed. So by preventing this from happening, we can prevent divergence, we get convergence. So that's kind of the how, but let's go back to the why a bit. Like, is this better? We are restricting the execution. Is this better than restricting edits? We argue that it is for a lot of applications. And it makes sense when you think about it. So suppose we go with an architecture here where instead of one thread having permission to edit, one thread has permission to merge in its neighbors. So in this case, every replica can continue to edit no matter who has this token. And if a partition or something occurs, they can keep on doing that. So every user using one of these replicas continues to have a local experience for their edits. And if this partition eventually ends, then the merges can keep on going and we haven't gotten stuck or anything. So there is a cost here. You're not blocked from editing, but what are you losing? And so it's kind of a different kind of cost, so we give it a new name. We call this staleness. So staleness is the measure of how old is the edit that I'm merging in. And it is a different kind of trade-off compared with consistency and availability. And we argue that it's preferable in applications like collaborative text editing, where you want this workflow of commit now, converge later. You want to see your changes happen immediately, and those can be resolved with other people's changes a little bit later. And if you think about this editing experience, it might be that this staleness, this fact that other people don't see your edits for a little bit, would be completely invisible. And that might be true. It kind of depends on how much staleness there is. And so to evaluate how much staleness is actually seen in practice, we have implemented Quark using OCaml and Shyla as a backend database that handles the distribution of versions between replicas. And our implementation performs merges in the background, so your application code is only dealing with editing. To evaluate this, this implementation, we have simulated a collaborative editing experiment where our application, where there's a text document that is being edited by many users. Each user has their own branch that they are merging into from other users' branches. And the users are making random edits at a human average speed of 4 per second. And again, this randomness is just covering the edits. The merges are happening as they are allowed in the background. And so for the experiment, we slowly increase the number of editors in this system. And as we do so, we measure the latency of the edits that are occurring and the staleness of the merges that are occurring. So these are our two measures. So we'll first look at latency. So latency, as we expect, is very low. Most edits take under 35 milliseconds because they're not depending on any communication with the other replicas. It's just a matter of writing to the database. So there is this kind of odd bump here that has to do with an idiosyncrasy in the threading implementation we used, but it is negligible. And that's really obvious when we look at the comparison of this to following a different rule set that imposes this only one thread can edit at a time behavior. So compared with that, it's clear that the only one thread can merge at a time behavior, the staleness, or the latency, sorry, is not at all dependent on the number of users. The more interesting results are the staleness. So we do expect staleness to increase with additional users, and that is what we see on this log scale graph here. But it is still low. For about 10 editors, which is pretty reasonable for a collaborative editing document, you have about 10 milliseconds of staleness. That's essentially unnoticeable. For 60 editors, you will have about 2 seconds of staleness. So that's not negligible anymore, but it is quite reasonable, especially when you imagine that this includes the time to write to the database and for network communication. And also, while you're waiting for your edit to be merged by others, you're not idle. You're continuing to edit. You're essentially pipelining this process of editing and then eventually merging. And you're also seeing the other merges of your peers. So your editing experience is never blocked. So to summarize, Quark is a runtime that ensures convergence for MRDTs. And it does so without requiring algebraic properties of the merge function that you're using and without ever delaying edits in the system. It does so by incurring a cost of staleness, which is a novel trade-off for distributed applications like this. And in practice, we show that Quark scales to many concurrent editors while keeping the staleness acceptably low. We have, of course, the implementation on GitHub if you want to take a look at it. And now I am happy to answer questions.
Okay, so So in your experimental setup, you have these database servers.
Mm-hmm.
So roughly, what's the round-trip communication latency between a pair of those servers in your setup?
It's low. So they're like co-located in a data center.
Okay. And are you where you're running the compute for the application? Is that in some virtual machine, in some
it's
container?
Amazon EC2 instances.
Okay.
I had essentially the same question, but I'm going to ask the follow-up, which is, did you run an experiment, since this is normally a setting where you'd have like geodistribution, did you run an experiment where the latencies between replicas were increased and see how that affected staleness, if it was linear or quadratic or crazy?
We have not done that. That would be an interesting experiment.
Thank you for the talk. My question is about the merge function. I'm a bit surprised by the requirement that it doesn't require any algebraic assumptions. So could you just give me some intuition about what happens, for example, if I have something that's not idempotent, like merging the same state with itself gives me something entirely different?
So I guess requirements for the merge function, it does have to be a total function, and it does have to be deterministic. But beyond that, convergence is guaranteed because our proofs don't rely on any assumptions about idempotency or anything like that.
Just want to take a minute to answer that question. So what we guarantee in MRDTs in this particular Quark implementation is just the convergence, right? Not the convergence to specific execution. So if your merge function is totally nonsense, then you do get convergence, but the convergence is to some nonsense value. So yeah, so that should answer your question.
Okay, so I guess let's thank Nicholas again.
Okay, thank you.